Hello, everyone. Welcome back. Today, we're going to be talking about unimolecular elimination, also known as E1. All right, and so this is the third in the lecture series of four that are the big four reactions. We've already talked about the two substitutions. Now we're going to talk about the two eliminations, starting with E1. And the thing about E1 is that I'll give the requirements first. It requires both a weak nucleophile slash weak base and it requires a good leaving group. And now you may think to yourself that sounds oddly similar to SN1. And funny enough, if I draw out the reaction conditions, right, this alkyl bromide here with methanol, that is the exact same as SN1. But the thing is, this generates, if we're doing an E1 reaction, these products. Okay? And so this is oddly similar to SN1, right? And the reason is because it is incredibly similar to SN1. It's actually the exact same reaction conditions. Okay? But what differs between this and SN1 is if we take a look at the mechanism here, what we would see is in the case of E1, we're ending up forming an alkene, right? This forms an alkene. So the question is how? Well, the answer for this specifically relies on the fact that if we think about the idea of what happens in SN1, right, the first thing that's going to happen is our leaving group leaves, generating a carbocation. All right, this carbocation is an empty p orbital. And if it's an empty p orbital, that means if we could give it electrons somehow, we could use it to make a pi bond by giving it electrons to form a pi bond between it and another p orbital. So how are we going to do that? Well, the way we're going to do that is through acid-base chemistry. Because if we take one of these protons here with our methanol, we come in, grab it, we can use the electrons here to form a double bond between those two carbons. And essentially what that's going to do is it's going to make the alkene for us. All right. So in this case, we generate those products. And the thing is, this differs quite a bit from SN1 in terms of enthalpy, right? Because if we're thinking about our delta H, the delta H of step one remains the same, right? It is always going to be that plus 68 kcals per mole when we're looking at a secondary bromine leaving group. But the second step is a little more interesting, right? Because now the delta H for step two requires multiple different factors, right? We are, for example, breaking a CH bond, right? That is the bond that we have to break in order to get the electrons to form the alkene. That being said, we are forming that CC double bond, and we are forming an OH bond. And remember, these BDEs are approximate, but they come out to being about plus 98. Forming is always going to be negative for us, so negative 65 and negative 102 gives us a delta H of step 2 equal to negative 69 kcals per mole. What this means is our overall delta H of the reaction, right, if we add these two together, is only negative 1 kcal per mole. And remember, this is entirely approximate because these BDEs don't exactly reflect what we're looking at, but it's just barely exothermic. Now let's compare this to SN1, right? So a reminder of what we saw in our SN1 reaction was that first step was the exact same, where the bromine left, and then the second step required us to form the bond between the oxygen and that carbon. And then the last step was enthalpically zero because it's just an acid-base reaction between the solvent and the actual molecule itself. All right. What this ended up giving us was step one's delta H was plus 68 kcals per mole. And then the delta H of step two was the formation of that oxygen carbon bond was negative 91 kcals per mole, to where our overall delta H of reaction, because remember the last step is zero, was negative 23 kcals per mole. So looking at this, you may say to yourself, okay, based on what I see here, if the delta H of the bottom reaction is so much more favorable, why wouldn't the top reaction ever occur? Well, let's take a look in terms of an energy diagram, right? Looking at an energy diagram of these two reactions, let's do blue being SN1 and red being E1. We're going to have to take a second to think about some things. So first, our reactants should be the same energy, right? We know based on what we just calculated that the product for the E1 is less stable than the product for the SN1, right? We just calculated the delta H's for that. But if we think about the intermediate for both reactions, we're going to ignore that last proton transfer for SN1 because it just adds more to our energy diagram. But for both of them, they share the same intermediate one, right? That is the leaving group leaving. So what this means is that for both of our reactions, this first step, where we go up this hill, is the exact same. Our second step, though, if we think about this, in one case, for the SN1, it is the attack of the methanol onto that carbocation. And that carbocation is very easy to get to. It's very quick. We talked about this a little bit last time in terms of that second step is very low activation energy. Now for E1, it has to kind of get up close and personal with stuff, right? There's a little bit of sterics that may be around that hydrogen. So overall, this one actually has a slightly higher activation energy, right? It's very slight though. So why would it ever favor E1, right? If the activation energy of the second step is less favored than the activation energy of SN1, why does it matter? Because we're essentially saying that E1 is thermodynamically and kinetically disfavored, right? So why would the reaction occur? There are two reasons for this. Number one, all right, our first reason is if we think about the activation energy peak for step one, right? Notice how it is much higher than the activation energy for step two. So we already have to put in all of that energy, right? And so it's kind of like if we're putting in that much energy, we effectively can reach any peak that is of that energy, right? So EA1 is much, much greater than EA2 peak. So enough energy is supplied to do E1 quickly or step two quickly. All right. So that's fine, but it doesn't explain exactly why you would still ever see much of E1, right? But the thing is, this energy, what we're doing right now is we're looking at it in terms of enthalpy. All right. So why does enthalpy matter and why did I distinguish that? Well, because funny enough, there is another term that matters for thermodynamics, entropy. So looking at entropy of SN1 and E1, all right, here's going to be a quick blast from the past. All right, in Gen Chem, ooh, I wrote in Gen Chem, you talked about delta S, right, which is entropy. And essentially, or the change of entropy, I guess. Essentially, what you found was that more disorder led to delta S being positive which is favorable. All right, there's your blast from the past because we're going to use that here in just a second. When we look at SN1 and E1, let's think about that step two, right? Because step one is always the same. All right, so for step two of these reactions, in the case of SN1, what it is our carbocation is getting attacked by the solvent methanol. All right, and that is generating this nice product with the positive charge on the oxygen. Versus in E1, what we're doing is we have our carbocation and we have this proton that's by it, where essentially our methanol is coming in, acting as a base, deprotonating that and forming the alkene. And so we end up with that and our protonated methanol as the conjugate acid. Here's the thing, when we're looking at these two reactions, for the first one, we start with two reactants, but we end up with only one product. All right? What this is doing is it is becoming more ordered, right? Because if we're going from two to one, that is more order, less chaos. So what that means is that our delta S for this specific step is negative. And if delta S is negative, remember it's the opposite of entropy, or sorry, enthalpy, it is disfavored. So entropically, this SN1 step is not favorable. E1, on the other hand, we start with two reactants, and we have over here two products. Essentially, what this is doing is it is the same level of ordered, which means that our delta S in this case is essentially zero, and that's relatively neutral for us. It's not disfavored, it's not essentially favored. Now then, the reason this matters is because you may remember another equation from Gen Chem, which is this one right here, delta G equals delta H, right, which we talk about delta H a lot, minus T delta S. All right, and so this actually contributes to our overall free energy. All right, it contributes to our overall delta G. And the other thing you'll notice that's very interesting about this is we also have this temperature factor that deals with delta S. And essentially what we're seeing is if delta S is negative in the case of SN1, that means the higher temperature is going to multiply with that to make delta S technically bigger, which means that it is going to become more disfavored at higher temperatures. All right, so higher T equals less favorable SN1. That's very important to keep in mind. That essentially says that higher temperatures will favor E1 due to the delta G. All right, but what we're saying here is that SN1 is enthalpically, which is based on our delta H, favored. However, entropically, so talking our delta S, it is disfavored. E1 by comparison, enthalpically, keep in mind it is technically still favorable, but it's less favored when compared to SN1. But entropically, it is more favored when compared to SN1. So what this does is the delta G's actually end up being incredibly similar, right? So these two ideas combined together, right? These cancel out each other, where our delta G is practically the same. What this means for us is that whenever we're doing this reaction of SN1 and E1, if the delta G is practically the same, we should end up with about a 50-50 mixture. That tells us that SN1 and E1 always occur together. All right? They are a pair. If SN1 is going to occur, E1 will also occur. Both products will be found in the solution. All right, so when we're doing these types of reactions, we have to keep in mind that one set of conditions actually manages to lead us to two separate sets of products. All right, and so keep this in mind when you're looking at these reactions because SN1 and E1 will always share the same conditions. SN1 and E1 will always occur together. Okay? That being said, we need to focus a little bit more on E1 because we already know how to get to SN1 products. Let's look at how we get to E1 products. And the way that we need to do this is we first need to understand what these eliminations are actually doing. And to do so, we need to understand alpha protons. Because notice that whenever we looked at that second step, I have always been choosing that when the methanol comes in and grabs a proton, it's grabbing this one over here, right? So the question becomes, if that is going to be the one forming our alkene, right? Why this proton, right? And what you want to do is think about octets and think about energy. All right, so think octets and energy. So when we're thinking about the step in terms of energy, the bonds that are broken are that CH bond, right, which is 98 kilocalories per mole. Whereas the bonds that we have formed the OH bond for 102 kcals per mole. And so if it ever grabs a hydrogen, it will give you some stability. But the thing is, you need the alkene to be formed. Because remember, when we're talking about this entire process, it just came out to barely exothermic. And the reason is because we have to have this C double bond C that gives us that extra 65 kilocalories per mole of stability, right? Both of these are required to be favorable by delta H. All right. So we have to form an alkene. Okay, so the thing is, if we're wanting to form an alkene, we have to then think about octets. Because looking at another place, this is where students like to take a proton from where the positive charge is, right? Logically, it feels right. You want to give a negative charge to where the positive charge is. But if we tried to do that, right, we have to form the CC bond, right? That carbon-carbon double bond. So we can't just break the CH bond and leave a negative charge or a lone pair on that carbon. Instead, we have to come in and we would have to form a CC double bond here. But the thing is, this is not possible, right? And the reason is because the adjacent carbon already has four bonds, aka a full octet. So looking at this, if we were to look at this in a Lewis form, right? So as a reminder, Lewis is drawing out all of these atoms. What we would see is this carbon with the positive charge, right? It has that proton connected to it that we could deprotonate. But the thing is, all of the atoms that surround it already have four bonds, right? They all have octets. So right here, we can't form a pi bond without the carbon with four bonds losing a bond. And that is why we choose to take the hydrogen from this adjacent carbon, because we get rid of one of its bonds so we can form the carbon-carbon double bond. All right. And so this brings up this idea of what is called an alpha carbon, right? And so this is the Greek alpha that we're looking at. What it's saying is that this is always the carbon adjacent to a functional group of interest. All right. So what this means is, let's say we're looking at a carbocation and we have a chain here. The carbon that the carbocation is on, this is just called the carbocation carbon, right? Very simply, it's telling you what's there. If we then move one atom out, we hit these two carbons here. Those are called alpha carbons, right? Because they are adjacent to the carbocation carbon, which is the functional group of interest. All right. If you move out another step, right, you just continue down the Greek alphabet. So this over here would be a beta carbon. And this would continue so on and so forth for as many atoms as you go out. Okay, and the reason this is useful is because later in the course we're going to talk a lot about things that have these alpha carbons. Because, for example, the reason that we say functional group of interest is because, say, we're looking at a carbonyl, right? We would say that the carbon right here, this is the carbonyl carbon, also known as the ketone carbon. And then looking one atom away, these would be the alpha carbons because they are alpha to the carbonyl. Okay? And the thing is, whenever we're looking at these alpha carbons with carbocations, they have this very fun thing on them called an alpha proton, right? So looking at where this hydrogen sits, it is on an alpha carbon, which means that this is an alpha proton, right? Anytime you have something attached to that carbon, it is technically inherits the name alpha. And what we see with E1 reactions is that only alpha protons can be deprotonated for an elimination reaction. So my recommendation to you is whenever you're going through and you're doing these eliminations, the first thing that you should do is you should think to yourself, what is the carbocation carbon, right? And just label that, and then go through and label all of the alpha positions, right? Because what we're going to see here in just a second is it actually makes a difference. And the reason for this is because of alkene stability, right? When we're looking at alkenes, they are a little interesting because alkenes essentially are two electrons shared between some carbons, right? We'll use this as a good example. So that pi bond is just two electrons shared amongst the carbons. But it's a little different from a sigma bond, right? Because in the case of this alkene, we can actually draw resonance forms. All right. We can draw a resonance form here that is essentially where we bring the negative charge and put it right here, and then we put a positive charge right there. Or we could also take these and we could draw a resonance form in the opposite direction, where we put a positive charge on that carbon and a negative charge on that one. And essentially what we see is these are not made the same, right? Because in both cases, we have what is essentially like a carbocation, right? And if it's like a carbocation, it can be stabilized by hyperconjugation. Essentially what this means is that this second resonance form right here, this resonance is technically more favorable, which means that the electrons are actually not distributed equally between the carbons, right? It's telling us that the electrons are actually skewed towards one side or the other. And so what this means is that the more stable we can make that sort of carbocation, in quotes, the better the alkene is going to be in terms of stability. All right. And so essentially what this means is due to hyperconjugation, more substituted alkenes are more stable. Okay. So looking at this as an idea of energy, right? We can draw a nice energy scale right here. And we're looking at this in terms of what has the highest and lowest energy. Well, we would say that the highest energy here would be an unsubstituted alkene, right? One that just has hydrogens on all sides. Because remember, hydrogens cannot provide hyperconjugation stability. The only thing that can is CH bonds that are adjacent. So looking a little further, if we were to attach a carbon on one side, that would be technically better. And we have names for these as we go from their substitution patterns. The top one would be unsubstituted. If you have one carbon, this is now mono substituted. All right, you can imagine as we go higher, or sorry, lower in energy, more stable, higher substitution patterns, the numeric changes. Right? The next one up would be a little bit of an unstable substitution with two different groups, right? This would be a Z disubstituted, right? Where di is essentially saying um, two. Next up, you can imagine, is going to be the more stable version of a disubstitution, the E disubstituted. All right. And then furthermore, as we go down in energy, if we have three things attached, we have tri-substituted. And then at the very lowest energy, we have tetra substituted. Okay. And so you can imagine that the more stable alkene is going to give us a lower energy of products. All right. And looking at this, just as a note, keep in mind that these can also have E and Z isomers. But as we discussed before, E is always more stable due to strain, or I guess less strain, right? Because remember that Z has those eclipsing interactions. Okay, so why does this matter? Well, whenever we're going to look at a elimination, right? Let's say we wanted to predict the product of a reaction, right? And let's just assume that this one only does E1 for our sake. Right, what we would see is that let's say we had a structure that looks like this, right? And we're doing an E1 reaction. What would the product be? Well, there are multiple options. And the reason for this is because if we think about the mechanism, right, the first thing that we do is the leaving group is going to leave, right? That bromine is going to leave on its own, and we end up with the carbocation. But looking at this, we have multiple different alpha carbons, right? And all of those alpha carbons have different alpha hydrogens attached. And what this does is it leads to multiple different types of products, right? If we were to take the blue proton, this one would be disub or tri-substituted, and it could actually be either E or Z, right? Because it has those two options in terms of forming the alkene, right? We could form the E alkene here, Or we could form the Z alkene. If we were to take from the red, what we would see is this one only has one option because what you end up forming is this weird looking disubstituted alkene right there. And then if we take from the orange, we have a different result where we have this tetrasubstituted alkene. And essentially, knowing alkene stabilities helps, but otherwise you would think which is the correct product, right? And the way we can determine this is entirely based on our energy diagrams. So back to another energy diagram, right? Looking at these different options, all of them start out at the same height in terms of reactants, right? So if our reactants are chilling up here, essentially step one is still always that big increase, and we get to our intermediate, and then from here they all split, right? We know based on our alkene energy scale that the highest and most unstable alkene is going to be the disubstituted one, right? So there would be our disubstituted alkene. Next up on the list would be we have some trisubstituted ones, but one is Z and the other is E. So those are going to fall into order in this way. And then last but not least, at the bottom of the ladder here is going to be that tetrasubstituted alkene, right? Because for that one, it's going to be the most stable because it has the best substitution pattern. And so what we end up seeing is that for these four different products, they essentially all go through what is a very similar activation energy, right? Incredibly similar, but they all end up with different final energies. And so all of them have different delta H's, where the most favorable, which is this one all the way down here, is the product, right? So the most stable alkene is the best to make. All right. So that being said, anytime you're doing this E1 reaction, you're always looking to form the most stable alkene that you can. Okay? The other thing is if we take into consideration, right, some stereochemistry, nothing matters. Because thinking about this reaction just in general, right, using our same methods as we did for SN1, if in the first step you end up generating a molecule that is achiral, then following that up with the elimination that we know can be chiral, right? We can form E or Z alkenes, but if it's always the most stable, then it doesn't make a difference in terms of the stereochemistry. You're always just forming the most stable alkene. All right, so essentially for E1, stereochemistry doesn't matter. All right, okay. Now then, hopping on to our next piece, which is the rate of the E1 reaction. Well, whenever we think about E1, it's the same rate determining step as SN1, right? Because notice even up here at the top when we originally referenced SN1 versus E1, notice how we talked about the activation energy of the first step's peak is so much higher than the activation energy of the second step's peak, right? Which means that it has the same rate determining step. So if it has the same RDS or rate determining step as SN1, that means it is the same rate as SN1, right? Because our rate is equal to K times leaving group leaving is the rate determining step, so it is just the molecule with the leaving group attached to it. And so that is once again a unimolecular rate, hence why we call it unimolecular substitution. The other thing that's the same as SN1 is solvent effects, right? We don't even have to say anything about it. It's the same as SN1. So if you forget what that is, go ahead and see lecture 23 notes. So E1 and SN1 are essentially the exact same in terms of what they can do, but one of them just creates a alkene, the other one actually does a substitution. Okay? So, with that being said, there is one thing that we didn't talk about in SN1 because we had to cover E1 first. All right, and that is rearrangements. So in SN1 and E1 in particular, we have an interesting phenomenon that occurs. So say we were looking at a molecule that looks like this, and we went through, we added in some ethanol, and we wanted to see what would happen. Well, what researchers found was that whenever they added in the ethanol and let it go and create the SN1 and E1 products, you would expect that the ethanol would substitute where the bromine is, but they found that interestingly enough, it adds over there. But that doesn't make any sense, right? Because that's not where the carbocation should be. So it should be impossible to do so. But then they also found that whenever they looked at the elimination product, it was also not between the alpha carbon and where the leaving group is. So how is this even possible? And what they found was it's due to rearrangements. So looking at the mechanism of this specific reaction, we see a very interesting rearrangement right in the middle. Because the first step is always the same, right? Leaving group leaves. The bromine is now gone. And so what we see is we have that carbocation sitting there. But interestingly enough, it can actually be moved around a little bit. Because this hydrogen that's sitting over here on this other carbon thinks to itself, you know what would be nice? Here in intermediate one, as we're going to call it, we have a secondary carbocation. But if I just move, if I take a little hop, skip, and a jump over here, we could actually generate a more stable tertiary carbocation for this intermediate two. All right. And what this does is now, if you think about it, it's not too hard to imagine. Of course, from here in SN1 would add the group onto that piece. And of course, from here in E1, the most stable alkene from the position that we're sitting at would be the tetra substituted with that alpha carbon. So these are occurring under those conditions, and it's clearly doing this shift, right? This is what we call a hydride shift, right? And what this hydride shift is doing is it's essentially the movement of an H to a carbocation to generate a more stable carbocation. All right. And so what this actually looks like in terms of energy is you can imagine in our energy diagram and our reaction progress, we won't draw out the whole thing, we'll just draw it through that hydride shift. If our reactants are here and we go up and we do our normal getting to intermediate one, remember this is our secondary carbocation. If the hydride shift occurs, what happens is that it just immediately drops down to where it is now a tertiary carbocation, which makes up for a little bit of energy, right? And this activation energy right here is practically meaningless, right? So the hydride shift has virtually no activation energy because it's within the same molecule that everything is occurring, right? And it's delta H minus, right? So it's favored. The important thing is that hydride shifts always occur if a more stable carbocation is available adjacent. Right? Keep in mind we're saying adjacent because that is a very important thing to keep in mind. Now then, that being said, if we want to look at an idea of what these look like, right, we're going to look at two separate short little reactions here. So some examples would be, let's say we were sitting on this secondary carbocation, and then we did a hydride shift. So taking this hydrogen, shifting it over to there, right? And remember the electron arrows for this is you're breaking that CH bond, you're forming the new CH bond. So we'll take a look at that in a bit more detail momentarily. But essentially, we now have that tertiary carbocation. So we're going secondary to tertiary. This would be favored, right? Because we're looking at an energy diagram where we start where the reactants are higher energy because that carbocation is less stable, and the products are lower energy because that tertiary carbocation is more stable. On the other hand, if we were looking at something such as this here, right? Let's say we want to do a hydride shift between this tertiary and this secondary. Doing so, we would be going from a secondary, but keep in mind this one is with resonance because remember these alkenes can do resonance right there, to a tertiary with no resonance. This would be disfavored, right? So this hydride shift could never occur because essentially this one would be going uphill. It would be endothermic and it has a much, much higher activation energy. All right. Same thing with the idea of if we were sitting on something like this secondary here, right? You may see the tertiary all the way over there and say, ooh, I want to start moving in that direction. So doing a hydride shift here would be a secondary to another secondary, which would be nice because another hydride shift would just get us to a tertiary. But in terms of energy, these are the exact same, right? And so reactant to product is great, but the thing is, it also takes quite a bit more activation energy. So overall, what we would see is this secondary to secondary is also technically disfavored by activation energy. Okay? So what does this mean for us? Well, it means that essentially, if we're looking at our least stable to most stable carbocations, right? As a reminder, the most stable would be a tertiary with resonance. That's better than the secondary with resonance, which is better than a primary with resonance, which is better than a tertiary, which is better than a secondary, which is better than a primary. Looking at this scale, it's also the direction of rearrangements or shifts, right? Because we're always moving towards the right-hand side, right? That is our direction of rearrangements. Okay, so keep this in mind when you're looking at these SN1 and E1 reactions. There may be more to it than what you immediately see. You need to check and see if you can form a more stable carbocation along the way in order to get to one of these positions where you have something that's a bit more stable and it will react in that way. Now, the other thing to keep in mind is that methyl shifts are also possible, right? What this means is say we have a situation such as this one. In this case, we have this very good quaternary carbon here. It would be nice if we could get over there to make a tertiary carbocation. It looks like we couldn't. But the thing is, these methyl groups can also shift, right? And so we would go from something that was a secondary, we added another carbon to where that carbocation was, and we have left only two carbons connected, or I guess still three carbons connected to that one. But now it has the carbocation, and so we went from what was essentially a secondary to a tertiary, which is favored. The only issue is it is slow, right? Compared to hydride shifts, where if we're going from a secondary to, whoops, I need to raise that in energy, to a tertiary, right? A hydride shift is very simple, very easy, right? So the blue would be H shift, and then the red will be RCH3 shift, right? In terms of an alkyl moving, it's going to be much higher in energy because you have all of that steric bulk that needs to move, and the bonds are much stronger. So the one thing to keep in mind about these is they don't happen often, right? Hydride shifts are more common, but these can occur if needed. All right. So let's do a couple examples of SN1 and E1 because we didn't do examples last time because we had to wait until we did this lecture because as you can see, essentially everything is tied together here. But let's do a couple of examples so that we can get an idea of what these reactions actually look like. So let's say we took this reaction here and tried it out. Water at 100 degrees Celsius, so we're refluxing it, alongside this nice molecule on the left here, which has a good leaving group. So as a reminder, when we're looking at SN1 and E1, the first thing that you should really think to look at is pay attention to where that leaving group is. Because as a reminder, SN1 can't occur on primaries, nor can E1 because they're both tied to the same reactivity. Thankfully, this thing is sitting on a secondary carbon. We do have our weak nucleophile slash base, right? Because they are one and the same. And so what we're going to see is that in our mechanism for this, it will be able to perform both SN1 and E1, right? First step of both of these reactions is that that leaving group is going to leave, right? Remember that this OTS is practically a sulfuric acid analog. So if it leaves, we end up with a carbocation that's in that secondary position. And now that we're here, we have to ask ourselves, okay, if we're sitting on this secondary, is there any adjacent atoms that would be better to put the carbocation on? We see that, oh, directly beside it, there's actually this tertiary. So it's a good idea to do a hydride shift to go from the secondary carbocation to the tertiary. right? It's much more favored. From here, now we have multiple paths that this can go down. All right, the first one that we can imagine is, let's say it does an SN1. All right, water comes in, attacks right here, and what that does is it generates this intermediate where the oxygen now has a positive charge with those two protons attached. And now we just need some more water to come on by, act as a base, and deprotonate it. So that's going to lead to our SN1 product, which is a racemic mixture of that OH right there. All right, so when we're looking at our original reaction, we would say that we have some of this alongside some of it where the oxygen is on the dash. So these would be your SN1 products, right? But as a reminder, E1 also occurs with these reactions. All right. So what would E1 look like? Well, essentially, we would take the exact same carbocation because that is where these reactions actually shift. And we have to ask ourselves, okay, where are our alpha carbons? All right. So we have three of them in this case, here, here, and here. Now we have to ask ourselves, which ones will form the most stable products? Which one has the most stable alkene possibilities? Well, if we do this one here on the bottom, this would be disubstituted, right, after forming the alkene there. Both of these on the top would give us some trisubstituted alkenes. So that tells us that, oh, hey, we're going to have to go and deprotonate the two that are up there. All right, so what this would look like is essentially, in one case, we would have our proton on the right-hand side. Some water would come in, it would do the deprotonation, you'd form the alkene, and we would end up with this alkene here. Keep in mind that the way that we've drawn this is to where this is E, right? Because remember that a Z alkene would be less stable. So having the trisubstitution here with it being E is good. For the other one, it's going to be the same idea, right? For this alpha proton, we have our water. It's going to come in, deprotonate that. We're going to form the alkene. And it's also going to generate an E trisubstituted alkene. So both are the same energy, which means that these are the E1 products here, right? So we have a total of technically four different products for this reaction, where the ones on the right are E1 products, the ones on the left are SN1 products. And remember, for SN1, all things considered, you could draw these as what we have drawn right down here, which is the racemic just line drawing, because the 50-50, we can approximate it as that. Okay, so that's an example of if we were to predict the products for an SN1 and E1 reaction that looks like this. Let's do another one. So for this one, let's say that we had a similar molecule. We use an iodide in this case, and we have this here. All right, thinking about this, we would expect, first of all, we have to check. We do have our iodide on a secondary carbon, and we have a weak nucleophile. Perfect for SN1 or E1. So, in terms of the mechanism for this one, step one is going to be our leaving group leaving. That is always true. So the iodine can just immediately leave. And we end up in a situation where now we have a secondary carbocation, right? But surrounding it, if we take a look to the left and the right, we have a primary and a secondary, right? Neither of these would be a good direction to move. So because of that, no rearrangement is going to occur in this situation. All right. That means that from here, we can split into our different paths, right? Where in one case, if we do SN1, our sulfur is going to come in, it's going to perform its nucleophilic attack. We have the SH, the positive charge, which means that more of it is going to come on over, deprotonate that, and we end up with our SN1 product, right? Which would be this one right here. Or we could take the pathway at the bottom where if we look at this and we ask ourselves, okay, where are our alpha positions? We have the two right here, where essentially, thinking about these two alpha positions, the primary alpha position would give us a monosubstituted alkene, but the secondary alpha position would give us a disubstituted alkene. So we're going to take from there. So essentially, in this case, our sulfur would act as the base, come in, deprotonate that alpha proton, make the alkene, and we end up with our E disubstituted alkene, which is our E1 product. So what that would mean is looking at our final products, we're not going to draw out the racemic mix of the SN1 product. Instead, we're just going to draw the bond line structure for it. We would end up with both of these as our final products. Okay? So overall, SN1 and E1, we're going to give a little bit of a summary for them, right? SN1 and E1 occur under the exact same conditions. So anytime you're asked about a reaction that includes SN1 or E1, you are essentially going to have to draw both products, right? You will not be allowed to just draw one unless there is a specific situation where one is not even possible. Okay? That being said, E1 always favors the most stable alkene. All right, so just remember that whenever you're doing these E1 reactions, that the product should be the most stable alkene that you can form from the alpha protons. All right, so remember to identify your alpha protons whenever you're doing these. Last but not least, rearrangements can occur to form more stable carbocations. Okay, so with that being said, SN1 and E1 are now complete, which means there's only one reaction left, and we'll talk about it next time. It is E2, and that will be the last of these big four important reactions that we've been talking about. We'll bring everything together at the end, and then there will be an additional lecture that's all about taking these and problem solving with them. So that being said, see you next time for the last in this little lecture series.